I will basically take over from where Aaron left, but before I go to that, let me just spend 5 minutes to make a brief recap so that everybody's on board. So we are talking about the conjecture that John Milnor raised in 1968, which predicted that for any smooth, complete, n-dimensional Riemannian manifold with non-negative Ricci curvature, the fundamental group should be finally generated. And the subject for today's talks is joint work with Elia Brouet from University Bocconi, Milan, and with Aaron, where we construct a family of counterexamples to the conjecture of Milnor. And more precisely, the shape of our counterexamples is the following. Let's start from a discrete group gamma, which is a subgroup of the rationals modulo the integers, which itself you should view as being a subgroup of the circle. For any such group gamma, we can find a smooth, complete, and 7-dimensional Riemannian manifold with non-negative Ricci curvature, and the fundamental group isomorphic to the group gamma we were starting with. So let me make the observation, which was kind of implicit in Aaron's talk, that even though if you are just interested in getting a manifold with fundamental group isomorphic to gamma, then you might just build the counterexample for Q mod Z itself and then look at the quotient with respect to the subgroup gamma. What happens is that the geometry of our examples and of their universal covers really depend on the specific choice of the group gamma we start with. So before I move on, let me also take 2 minutes to briefly review the state of the art and mention the obvious open question about the Milnor conjecture. So as Aaron explained, the Milnor conjecture, well, it's obvious in dimension 1. It's true in dimension 2 due to the classification of surfaces with non-negative Gaussian curvature obtained by convulsing in the 30s. It's true in dimension 3, thanks to the more recent work of Gangliu, again classifying complete 3-dimensional Riemannian manifolds with a negative Ricci curvature. And let me also mention, again, the previous work of Shane and Yao in the 80s, who dealt with the case of Ricci curvature strictly positive, and more recent work of Pan, who does not give the complete classification of 3 manifolds with a negative Ricci curvature, but still gives a quite distinct proof of the Milnor conjecture in dimension 3. On the other hand, there is the obvious extension of our 7-dimensional counterexamples to any dimension greater or equal than 8, just by taking the product of our counterexample with the Euclidean factor of their nth dimension. And this leaves with the obvious open question about the validity of the Milnor conjecture in dimension 4, 5, and about dimension 6, we have the upcoming work joint with Elia that Aaron already mentioned. So this is a brief outline for the rest of my talk. So the introduction is over. What I'm going to do first is I'm going to review in a little bit larger generality the topological construction of the counterexamples. And then large part of the talk is going to be dedicated to explaining how one of the key geometric steps is constructed, one of the key geometric steps that Aaron alluded to in his previous talk. And in the last 10 minutes or so, I would like to discuss the asymptotic geometry of our counterexamples, both of the quotient guys and both at the level of the universal covers, and to illustrate how it fits together with the known restrictions linking the asymptotic geometry of manifolds with non-negative Ricci curvature with the finite generation of fundamental group. And I will mention a few open questions more if I have still time at the end. Of course, feel free to interrupt me at any time if you have questions or comments. So the construction, as Aaron explained, is going to work at the level of the universal cover, which in the end, we would like to be a complete, smooth, 7-dimensional Riemannian manifold, and with the metric of non-negative Ricci curvature, and with the properly discontinuous group action by the group gamma we start with. And the construction is going to be inductive. I'm going to comment later on the inductive steps. However, before we move to the core of the construction, we need some at least algebraic preparation. So let's start from any group gamma, capital gamma, which is sitting inside the rational numbers modulo the integers, which again we are viewing as being a subgroup of the circle. And we fix a sequence of radii. They are scales. They are going to plus infinity, and they're going to plus infinity very, very fast. I'm going to comment in a few seconds on the role of this sequence of scales in the picture, in the geometric picture of the counterexamples. So it's elementary to check that any such group gamma can be written as a nested increasing union of finite subgroups. And for each finite subgroup of the circle, it's again elementary. It's obvious to check that it's obvious that each such subgroup of the circle is going to be generated by just one guy. I'm going to denote by little gamma I, the generator of the group capital gamma I. And again, it's elementary to check that for any such I, you can find a parameter, an integer ki, such that the new generator, little gamma I, raised to the power ki, gives you back the old generator, little gamma I minus 1. So in order to reconciliate with the example that Aaron discussed, let me make the observation that if we choose little gamma I to be 2 to the minus I in the previous general construction, then the parameters ki in the construction are all equal to 2, and the resulting group that you get is the group of the dyadic rational numbers modulo the integers. Okay, one comment concerning the relationship between the scales Ri and the subgroups gamma I of the infinitely generated group capital gamma. So it turns out that the way the construction works is that in the end, the finite subgroups capital gamma I are going to be local fundamental groups of the manifold M, where in this case, by local fundamental group, I mean that capital gamma I is going to be the subgroup of the fundamental group of the full fundamental group gamma in the end, generated by those isometries in the universal cover, which displays a fixed base point, a distance less or equal than Ri, where Ri is one of the scales that I fixed at the beginning of the slide. Okay, very well. So as Aaron was explaining, all the focus of the construction is on the inductive step. But before we move to the inductive step, let me spend a few minutes to describe, to try to give you a global picture and to describe the tree that Aaron already mentioned in this talk. So the perspective that I would like to adopt in order to introduce the tree is the following. So the construction of the tree is almost elementary. You start from a bunch of half lines. These half lines are going to be indexed by the group, discrete group gamma we start with. So you are staring at the cross product gamma cross 0 plus infinity, where 0 plus infinity denotes my half line. And the way you build the tree out of it is by defining an equivalence relationship whose role is going to be to collapse different branches of these half lines together in order to give you a tree in the end. And the equivalence relationship that we will define is very simple. I'm going to stipulate that the pair little gamma, little t is equivalent to the pair little gamma prime, little t prime, provided the difference of the, let's say, spatial components belongs to one of the groups capital gamma I, and their time components, they are equal, and they are greater or equal than the scale at which the group capital gamma I kicks in. Okay, so let me also make the observation that there is an induced action of the group gamma on this tree, which is the action induced by taking the quotient of the natural action of the group gamma on the cross product by multiplication on the first factor. So it's elementary to check that this action goes to the quotient, and this induces an action, a geometric action of the group gamma on the tree we were staring at. On the bottom, you can see a picture of a small part of the tree. So the picture that you should keep in mind is that the tree starts at the bottom level, and it goes up forever on the top. Each layer of vertices in the tree is going to be indexed by one of the quotients capital gamma modulo capital gamma j. And now in the picture here, in this specific picture, you can see the picture of the tree where this step from green to red corresponds to taking the parameter kj equal to 4. So you have 4 vertices, 4 green vertices going into each red vertex. And then the next step corresponds to the choice little kappa j plus 1 equal to 2. Okay, so what's going to happen is that we would like to get the manifold in the end, and what you need to do, as Aaron was explaining, to get the manifold out of the tree in this global picture, let's say, is to replace each vertex in the previous slide of the tree with a copy of the free sphere across the 4 disk, and all the edges of the tree are going to correspond to gluing along boundary components of these copies of manifolds with boundary. And the way you should picture the gluing is that each copy on the bottom line, let's say, of S3 cross D4, each copy corresponding to each vertex is going to glue into another copy of S3 cross D4 corresponding to the upper layer of vertices by removing a small copy of S3 cross D4 from the top guy and gluing together the S3 cross S3 boundary components with a diffeomorphism mapping the bottom boundary component to the upper boundary component. So, however, for the rest of the talk, the focus is going to be on the inductive step. The induction is going to work in the following way. We would like to build a sequence of manifolds they're going to be in the end complete, smooth, semi-dimensional Riemannian manifolds, which are simply connected. They are endowed with the metric with non-negative Ricci curvature, and they have a fixed base point, and each manifold, capital MJ, is going to be endowed with the properly discontinuous group action by the discrete and finite group capital gamma J. And the focus for most of the talk will be on the inductive step, where we, let's say, start from capital MJ, modify a little bit, and do some gluing operations in order to get an extended manifold MJ plus 1. And during this extension step, we not only would like to extend the manifold to a new guy, to modify the manifold and get a new guy, MJ plus 1, but our main goal will be also to extend the action of the group capital gamma J to a new action of the group capital gamma J plus 1 in a, let's say, compatible way. And the induction will be set up in such a way that in the end, at least at the moral level, roughly speaking, the end guy, the end universal cover, together with the group action of capital gamma, is going to be, roughly speaking, just the limit of the guys that you build at the earlier steps of the throughout all the steps of the inductive construction. So here is a picture that is meant to illustrate how the inductive step of the induction works. So in the inductive construction, what's going to happen is that we are going to pick Kj, which in the picture is equal to 4 copies of the manifold that you build at the step J minus 1 of the induction. We are not quite sure yet that what's the topology of these guys. However, by the way the induction works, we are sure at this stage that the ends of each copy of the unique end of each copy of the manifold Mj minus 1 is diffeomorphic to an annulus in D4, an annulus in R4, cross an S3 factor. And what we are going to do in order to get the extended manifold Mj is we are going to put a new copy of the S3 cross D4 on the top of the old guys. And in order to prepare for the gluing, what we are going to do is, let's say that the new copy on the top is the blue guy. We are going to remove 4, corresponding to our choice of Kj in this picture, 4 copies of the 4 disk from the blue big 4 disk. We're going to remove 4 copies of the disk from the big guy. Those 4 disks come together with a cross S3 factor, and this is going to leave our top guy, D4 cross S3, with 4 new boundary components, 4 lower ends, if you prefer. And these ends are still of the form annulus in the 4 disk cross an S3 factor, and therefore they are compatible with the ends of the manifolds Mj minus 1 that we get at the step J minus 1 of the induction. And therefore, it is at least possible to glue them together. However, in order to specify the topology of the resulting guy from the gluing, I need to tell you how these ends or these boundary components, if you prefer, are glued together, the new boundary components in red that you created from the cutting out procedure. And Aaron was explaining this. It turns out that these gluing maps are going to need to be very non-trivial, and how non-trivial they are is going to be dictated by the choice of the action. Because remember, one of our goals is not only to extend the manifolds Mj minus 1 to new manifold Mj, but together throughout this process, we would also like to extend the action. So my next goal is to briefly recall you how the action is going to behave on the top guys. So remember that the manifolds Mj minus 1 come together with an action of the group capital gamma J minus 1. And what I'm left to do in order to tell you how the extended action looks like is to define the action of the new generator, little gamma J, on the new copies, the blue guys that we added on top of the old guys. And the way the construction works is that we stipulate that the action of little gamma J, the new generator, on the new copies, the blue guys of S3 cross D4 is going to be by Hopf rotation with angle 2 pi over this product on the S3 factor. And let me notice that this product is nothing, by the very algebraic construction, is nothing but the order of the element little gamma J, and it's gonna rotate along a Hopf fiber with angle, or rotational angle equal to 2 pi over the much smaller integer Kj on the D4 factor. Now, here is where the non-triviality comes from. So let me comment on the fact that you can view this discrete action as being a sub-action of the circle action, which are going to denote in the sequel as being the 1, k1 dot kj minus 1 of action. So it's a circle action, which is rotating with speed 1 on the S3 factor, and it's rotating with a much bigger speed, this product on the op fiber of the S3 factor, which is the cross-section of the D4 component of the manifold. So here is where the non-triviality comes from. Now, remember that the way the construction works is that it needs to be compatible with what we have done at the earlier steps of induction. Now, if we unwind the definition above, it's elementary to check that the action of little gamma j to the power kj, which by the algebraic construction is nothing but the whole generator little gamma j minus 1. By the way I defined its action on the top guy, the action of this element, this isometry, is going to be just by pure rotation on the S3 factor. The reason for which this is true is that taking the kj power is going to completely kill off the rotational component on the D4 factor, while we will be left with the rotational component of the S3 factor. However, by the way the induction is set up, the action of the whole generator little gamma j minus 1, which is the generator of the group capital gamma j minus 1, should be induced by a mix of rotational action on the ends of the guys that we glue by the inductive hypothesis, let's say. And therefore, if you unwind all this, Aaron already explained this, this is telling you that the gluing diffeomorphism that we need in order to make this construction really meaningful, in order to get a well-defined global action, what we need for the gluing diffeomorphisms is that they should conjugate the two actions, the mixed rotational action rotating on both components, the 1, k1, kj minus 2 in this specific step of the construction. They should conjugate this mixed rotational action just with the pure rotational action acting on the free S3 factor. Okay, so let me make a brief recap and stress again the main challenge that we need to face in order for this gluing to work. So the setup is the following. We have that each end of the manifolds that we got at the earlier steps of the inductive construction, so the single end of the manifold capital M j minus 1 is diffeomorphic to S3 cross an annulus in R4, which we will view later as being S3, at least topologically as being S3 cross the cone over S3, and therein the action of the whole group capital gamma j minus 1 is by mixed rotation on both S3 factors. Now, what happens is that by the cutting off procedure on the new copy of S3 cross D4 with the several copies of S3 cross D4 removed, we created new bottom ends, let's call them bottom ends or lower ends. And these lower ends, they are topologically compatible with the ends of the old manifolds mj minus 1. However, the action is not compatible at first sight because the action of the restriction of the action of the group capital J minus 1, gamma J minus 1 to those ends should be by pure rotation on the S3 factor there. The challenge that we need to face is that we would like to twist, let's say, roughly speaking, the ends of the old guys mj minus 1 to turn a mixed rotation on both factors into a pure rotation on the S3 factor. And the main source of troubles when we would like to do that is that we would like to do this twisting in a Ricci non-negative compatible way. So that's the end of the review of the topological construction. Maybe it's a good time for questions, if you have any. Okay, if not, I'm gonna start describing the construction, how this gluing is performed geometrically. So the picture that you should have in mind for this gluing step is that the gluing is not gonna happen straight away. It's gonna happen on a neck. And this neck, at least topologically, is gonna be very simple. The neck is gonna be diffeomorphic to S3 cross an interval. So it's gonna be, let's say, a cylinder over S3 cross S3. However, we will use two systems of coordinates on this neck. We will use the green system of coordinates in this neck, which is simple, let's say diffeomorphic to S3 cross an interval. And in this green system of coordinates, which is the one coming from the bottom end, let's say, what we are going to see is the 1k mixed rotational action. The specific value of k does not play any role here. So in the green system of coordinates, that's the picture that you should have in mind. So you see S3 cross S3 slices where the action is mixed rotational on both components. And you take the product with the interval on the left-hand side. On the right-hand side, we are going to use the red system of coordinates, and the effect of this change of coordinates is going to be to turn a mixed rotation on both components into a pure rotation just on the left S3 factor. So the effect, at least if we just care about the topological point of view, the effect of the change of coordinates is going to be to turn a mixed rotation on both factors into a pure rotation on a single factor, S3 factor. So that's the topological picture that you should have in mind. The geometry picture turns out to be a little more tricky because remember that this gluing should be compatible with the geometry we would like to endow with our guy at the end. And moreover, that this gluing is going to be quite restricted in the sense that we would like to endow the neck and all the manifold in the end with the metric of non-negative Ricci. So if you go back to the previous slide, the topological picture was very simple. The effect of this change of coordinates was to turn a mixed rotation on both factors into a pure rotation on both, just on a single factor. However, if we care about the geometry, what we should keep in mind is that the geometry on the bottom, on the neck, is going to be dictated by the geometry which is coming from the earlier steps of induction. And just to simplify a little bit, we could assume that the geometry on the bottom of the green guy should be the standard product geometry of two round S3 factors. However, as I was saying, and as Aaron explained, in order for the next gluing, we will be using a different system of coordinates, which is the system of coordinates which is turning a mixed rotation into a pure rotation. And therefore, what we would like to get is that the geometry is simple in the new system of coordinates. So in the red column, we would like to see a simple geometry at the end of the gluing neck. So in order for this to be possible, as this the expectation is that this diffeomorphism is going to be highly twisting, we would like the green geometry on the end of the neck to be the pullback with respect to the diffeomorphism, the change of coordinates, the diffeomorphism of the very simple geometry on the upper end of the red guy. And this is telling us, this is suggesting to us that on the end of the green guy, we are going to see a very, very complicated geometry, at least before we identify it with the simple one with the diffeomorphism. And so our challenge for the next few minutes is going to be the possibility proving that it's possible to connect this very twisted geometry that we get by pulling back the simple one with the twisting diffeomorphism capital phi with the standard geometry that we see on the bottom of the neck. Are there any questions on this picture? Okay, if not, let me state the main technical proposition that we need, which is the proposition dealing with the action twisting in relationship with the multiple class group that Aaron was alluding to. So I'm going to state the equivariant version of the statement, and then I'm going to see as I'm going to show you as the non-equivariant version of the statement that Aaron stated follows as a corollary from the equivariant one. So the precise proposition is the following. We start from the standard product of two round metrics on S3 cross S3, and we fix any integer. Then the statement tells you that there exists a diffeomorphism phi from S3 cross S3 into S3 cross S3, and there exists a smooth family of Riemannian metrics on the product of the two three spheres with the following three properties. So the first property is that you would like each of these metrics on the radial slices of the neck to be positively Ricci curvature. Moreover, you would like the construction to be equivariant with respect to the 1K rotational action, in the sense that the S1 1K mixed rotational action should be isometric for each time with respect to this matrix GT. And moreover, what the picture was suggesting in the previous slide is that the end geometry, in the end Riemannian metric G1, should be the pullback of the standard round metric on S3 cross S3 with respect to a twisting diffeomorphism, which we would like to conjugate the mixed 1K of faction with the pure rotational 1,0 of faction. So if you want to get a little bit of familiarity with this statement, I think it's quite instructive to try to do an analogous construction for a family of flat Riemannian metrics on the two torus. Okay, so let me briefly comment on the gluing diffeomorphism, on the twisting diffeomorphism that we get from the application of this statement. So it turns out that at least up to isotopy, and at least in a case where K is equal to 1, which corresponds to the case where you want to conjugate the 1-1 of action mixed on both components with the same speed to the pure 1-0 action. At least up to isotopy, we can get a clean expression for the conjugating diffeomorphism, which is the one in the displayed formula, where I'm viewing S3 as a group. And the key remark to keep in mind is that for general K up to isotopy, we cannot get such a clean expression for the twisting diffeomorphism. However, what turns out to be true is that each of the twisting diffeomorphisms has the following special structure. You can take it to be up to isotopy, the identity on the first component, and you can take the second component to be a rotation on the second component with respect where the rotational angle, let's say, depends on the first guy, smoothly, of course. And two comments on this quite explicit gluing diffeomorphism. So first, there is the comment that Aaron already pointed out, which is the fact that this gluing diffeomorphism, that's pretty easy to check in the case of the explicit guy for K equal to 1. They are not isotopic to the identity. It's an exercise to check that the guy in the displayed equation is acting non-trivially on the free homology of S3 cross S3. On the other hand, even though they are not isotopic to the identity in general, what turns out to be true is that any such diffeomorphism by the second displayed equation trivially extends to a diffeomorphism of S3 cross D4 into S3 cross D4, just by radial extension on the second component. Now, let me come to the non-equivariant corollary that Aaron mentioned. So the corollary is the following, and it deals with the action of the mapping class group of S3 cross S3 on the standard round metric inside the space of metrics with positive Ricci curvature on S3 cross S3. The precise statement is the following. You can start from the standard product of two round metrics on S3 cross S3, and you can pick whatever diffeomorphism from S3 cross S3 into itself. Then our theorem tells you that you can find a smooth family of Riemannian metrics, GT, on S3 cross S3, with the following two properties. First property, you would like the Ricci curvature of all the metrics in the interpolating family to be strictly positive. And the second property is that you would like the n metric to be the pullback of the standard round metric with respect to the diffeomorphism you were starting with. So, of course, Aaron already discussed this. The theorem is trivial in the case where the diffeomorphism is isotopic to the identity, and the construction is completely elementary. In that case, you can fix an isotopy, little phi t, between phi and the identity, and you can take the metric GT, the interpolating family of metrics, to be just a pullback of the standard round metric with respect to the diffeomorphism phi t at the time t. On the other hand, this should be clear, what I remarked in the previous line. So it turns out that the diffeomorphism group of S3 cross S3 is not path connected. And what's more remarkable is that the diffeomorphism coming up in the previous slide, they are, even though the diffeomorphism group is not path connected, these guys coming out of the equivariant statement, they are enough to generate the mapping class group of S3 cross S3. And that's the way the non-equivariant statement follows from the equivariant statement. Are there any questions on this?
So for your later construction, would it be, I mean, just theoretically, would it be enough to get a positive Ricci curvature metric on S3 cross S3 cross the interval, so that you kind of replace this homotopy of Ricci positive metrics by a concordance? So sometimes,
let's say that if the boundary conditions are nice,
yeah,
that would be enough. That will be enough.
But probably it doesn't help you, I guess. But it's just
at least so that was like it was easier maybe in this way, but at least theoretically you are perfectly right. It would be enough to get a bordism between the two guys,
exactly.
And to get a metric with non-negative Ricci curvature meeting the expected boundary conditions, let's say, on the neck connecting the two. Yeah. It's not the fact that the neck is topologically trivial. Let's say it's a cylinder, does not play any role in the future construction.
Okay. Yeah.
Of course, you would like the guy to be equivariant with respect to the discrete action. That's the other requirement that you would like to meet. Any other questions or comments? Okay, if not, for the next few minutes, I would like to give you some more details about the construction of this interpolating family of metrics. And in the end, we will see how one can construct the neck with non-negative Ricci curvature, starting from the family of interpolating metrics with positive Ricci curvature. And it turns out that in order to build the interpolating family of metrics, it's relevant to understand quite well the iterated bundle structure of these guys. So let me start with some easy remarks. So we are going to view the S1 action mixed of rotational action as a multiplication action on the left. And if you view the S1 action as being a multiplication on the left, then it's elementary to check that there is a commuting right action of the group S3 on S3 cross S3, which is just the right action by multiplication on the right on the second S3 factor. This S3 action turns out to be commuting with the S1 action. And moreover, you can also check that, let me denote by capital N, the quotient of S3 cross S3 with respect to the 1K of action. Then it's also elementary to check that the induced S3 action that you get on the quotient is still free. Moreover, what's also easy to understand is that if you take the iterated quotient and you first quotient, or in whatever order, you take the quotient with respect to the S1 action, and then with respect to the S3 action, the resulting of this iterated quotient is going to be standard S2. The reason for this is that if you, let's say that we do the quotient with respect to the S3 action first, this is going to completely kill off the second S3 factor, and therefore, and then we are just left with the off action on the first guy, and it's well known that the quotient of the S3 factor with respect to the off action gives you back an S2. Now, the immediate consequence of this observation is that the 5-dimensional quotient M, so the manifold capital N, gets an induced structure of a principal S3 bundle over an S2 base. And it's well known that there are not many of them. In particular, there is only the trivial one, which is also buying us for free the diffeomorphism of the manifold N with S2 cross S3. It's going to turn out that the Riemannian matrix G0 and G1 and all the Riemannian matrices in the interpolating family are going to respect this iterated bundle structure. And that's the picture that you should have in mind at the diffeo level. Let's start discussing the picture at the geometric level. So let me introduce a piece of terminology. I'm going to denote by H0, and this is going to be, of course, H0 depending on K, the induced Riemannian metric on the quotient of S3 cross S3 with the metric G0 with respect to the 1K action. And analogously, I'm going to denote by H1, which we are going to see in a second is not going to depend on K. Actually, the quotient of the N metric G1 with respect to the 1K action. So the easy remark is about the shape, let's say the geometric shape of the metric H1. Indeed, it turns out that up to isometry, this follows from the fact that the N guy is going to be equivariant to a standard geometry on S3 cross S3 modulo the S1 action just acting on the op fiber of the first S3 factor. The consequence of this observation is that this quotient geometry on N5, which we already remarked is diffeomorphic to S2 cross S3, is isometric to the standard product geometry on S2 cross S3, where the first guy is endowed by the metric coming from the op quotient, which is the standard metric where the sphere gets the radius 1/2, say for the sake of normalization that the round metric on the manifold S3 had the radius equal to 1, and we get the product with the standard round metric on the S3 factor. The picture turns out to be a little more tricky at the level of the first quotient, because this circle action, this mixed circle action rotating on both components is a bit more complicated geometrically. And the first picture that you would like to focus on is already suggested by the fact that when K goes to plus infinity, this single circle is going to become denser and denser into the two torus where it sits in. And this is already suggesting that the expectation is that the quotient geometry should converge in the Gromov-Hausdorff sense to something lower dimensional. And indeed is going to converge to the full quotient of S3 cross S3 modulo the op function on the first S3 factor and the op function on the second S3 factor. So the N geometry that we will get if we take K going to plus infinity is going to be the standard product geometry of two round geometries with radius 1/2 on the two lower dimensional S2 spheres. Let me also make the observation that this is a very interesting example of collapse with bounded sectional curvature and uniformly positive Ricci curvature that has already been discussed several times. It appears several times in various forms in the past literature. And this should give you a feel about how complicated the behavior of these geometries is going to be, at least when k goes to plus infinity. And my goal for the next slide is going to be a bit more precise about the geometry of these quotients and of the total spaces. Are there any questions or comments on the previous slide?
Yeah, hi. Could you say something about the curvature of the quotient metric on S2 cross S2?
On this S2 cross S2 or on the S2
Yeah, is that something that you also worked out, or maybe you're going to talk about that next?
I'm not sure I got your question. Like, would you like to know something more about the curvature on S2 cross S3, the induced?
I mean, if the induced limit metric on the quotient S2 cross S2 has some special upper bound, like lower bounds on the curvature, so that you know that the Ricci curvature is strictly positive, or something like that. There's also the Hopf conjecture. I don't know if you know about that on like S2 cross S2.
I'm not sure I understood completely your question. So the geometry on this limit guy is going to be standard. So it's going to be the product metric of two round metrics on each S2 factor. I don't know if this answers to your question. Okay, so in particular, you can easily compute the curvature of these limit guys. And of course, this is not going to have a positive sectional curvature. Okay. Any other questions or comments? Okay, if not, let me describe more in details the geometry on the total spaces and on the quotients. So we are going to display in the next table the relevant geometric quantities for understanding this geometry on the iterated S1 bundle over the S3 bundle over the base space S2, both for the initial time t equal to 0 and from the end time t equal to 1. So let's start reading this table from the bottom, which is the easiest line. So it's easy to check that the metric on the total space of the iterated quotient is going to be standard round metrics with radius 1/2, both for t equal to 0 and for t equal to 1. Let's move to the upper rows of the table. So the easiest one to understand is the right column. So we already remarked that the quotient geometry on the 5-dimensional guy is the standard product geometry of an S2 with the right radius with an S3 with the right radius. And therefore, at the level of the bundle geometry, it's elementary to check that the second fundamental form of the S3 fiber is going to be vanishing. So the fibers are going to be, of course, totally geodesic because we are staring at the product geometry. The induced metric on the S3 fibers is going to be just round, and the connection on the S3 bundle is going to be topologically trivial, but much more than that is going to be flat. On the other end, the remark that I made on the previous slide should suggest that this picture should be much more complicated at the level of the left column. What turns out to be true is that the fibers of this bundle geometry are going to still be totally geodesic. However, when we look at the induced metric on the S3 fibers, this is not going to be round anymore. And the shape of these fibers is going to be that of Berger spheres, where one of the directions is shrunk with respect to the others. And moreover, we get some non-triviality even at the level of the connection. The connection is, of course, trivial from the topological perspective, because as I already remarked, that this bundle is going to be topologically trivial. However, this connection is going to be non-trivial from the geometric perspective, meaning that it's going to be non-flat. Now we can move to the study of the S1 bundle. So at the level of the S1 bundle, the easy observation is that the fibers of this S1 bundle, which are the 1K circles for time t equal to 0, and they are just the 1,0 circles for t equal to 1. In any case, the length of these fibers is going to be constant for both times, and a computation is going to tell you that the connection of both bundles is going to be in Coulomb gauge, which means that the divergence of the connection one form is going to be 0, and moreover, this connection is going to be Yang-Mills, which means that the curvature induced to form is going to be harmonic with respect to the base geometry, both at the level of t equal to 0 and at the level of t equal to 1. Okay, so now we would like to interpolate between the original metric G0 and the end metric G1, and we are going to do that in 2 steps. The first thing we are going to do is to build a family of interpolating metrics on the 5-dimensional guy N, corresponding to the S3 bundle over S2. And the way we are going to build that is basically suggested by the table that I showed you in the previous slide. So let's start again from the bottom row. So the geometry on the S2 base was round at the beginning, it's round at the end of the deformation, and there is no reason to modify it throughout the deformation. So we are going to keep the metric on the base S2 guy fixed throughout the process. On the other end, so let's discuss briefly what happens at the level of the second fundamental form. Again, in this case, the fibers are totally geodesic at the beginning of the process, and they are totally geodesic at the end. And there's no reason, again, to break this symmetry. And so we are going to keep totally geodesic fibers throughout the process. The non-triviality comes from the fact that we had a no-round metric at the beginning, and we would like to connect it with the round one. And we had a non-flat connection at the beginning, and we would like to connect it with the flat one. However, there is an easy fix for this asymmetry. Let's say what we are going to do is we are going to first round off the metrics on the fibers, and we are going to pass from the asymmetric Berger metric to a symmetric round beam variant metric on the S3 fibers. Once this has been done, we are going to interpolate between the non-flat connection. We are going to just take the affine interpolation between the non-flat connection that we get at t equal to 0 and a flat connection whose existence we know from the topological triviality of the bundle. And the remark in regard of this deformation process is that it has been understood for a while, from the 70s at least, that as soon as the metric on the fibers, on the S3 fibers throughout this interpolation is shrunk enough, the resulting S3 bundle over S2 is going to have a Ricci positive for all times. Any question about the deformation of the 5-dimensional guy?
So does this follow from some O'Neill formula? Or
that's correct, exactly. It follows from the Riemannian subdimensional formulas.
Okay.
Okay, any other question? Okay, if not, we can move to the deformation of the metric on the total space of the S1 bundle. The deformation of the metrics on the total space of the S1 bundle turns out to be a little bit more subtle, and the reason you can easily imagine. The reason is the fact that the flat S1 fiber is contributing to zero curvature at the very least. However, again, the picture for the deformation from t equal to 0 to t equal to 1 is again suggested by the table that I showed you in one of the previous slides. So what we're going to do is we had a connection which is Young-Mills and in Coulomb gauge for t equal to 0, and we want to get in the end to a connection which is again in Coulomb gauge and Young-Mills, which, let me remind once more, means that the divergence of the connection one form is 0, and that the divergence of the curvature to form is 0. And the maybe easiest choice is for any intermediate time to look for the unique connection which is in Coulomb gauge and with divergence-free curvature, which means Young-Mills, in the right cohomology class for all times. This is going to fix a connection for our bundles, and the last piece of information that we need to determine in order to determine the Hull metric of the guy is the size of the fibers. So it would be reasonable to expect or to hope that one can take the length of these fibers to be constant for all times, because it is constant at the very beginning and it's constant at the end. However, this turns out it's not completely clear if this is possible, and this is related to the expression for the Ricci curvature in the directions tangent to the S1 fibers coming from, again, from the formulas for the curvature of Riemannian submersion. So let's have a look at the formula for the Ricci curvature in the directions tangent to the fibers. So I am denoting by little f the length of the S1 fibers, and by denoting by omega the curvature to form of the bundle, which has been fixed by this unique choice in the bottom two lines of the table. So the formula for the Ricci curvature has the expression displayed in the slide, and your enemy here is the possibility that the curvature to form, which does not vanish at the very beginning and it does not vanish at the end, and for topological reasons you know to be non-vanishing at least somewhere. So your only enemy to the possibility of taking f equal to a constant throughout this interpolation is the fact that it's not completely clear a priori that this curvature to form should be everywhere non-vanishing. However, an idea which we borrow from a paper by Gilkey, Park, and Tushman at the end of the 90s is the fact that even though you don't know that this curvature to form is strict as modulus strictly positive everywhere, it's possible to choose to make an appropriate choice of the warping function f in order to get positive Ricci curvature on the total space of the S1 bundle, with the only condition that the bundle is non-trivial, which is going to provide you the non-triviality of the modulus of the curvature at least somewhere on the manifold. Okay, any questions on this second step of the interpolation? Okay, if not, I'm left to tell you how to get the metric with the negative Ricci curvature on the neck, starting from the family of interpolating metrics on the radial or time slices, whatever. Okay,
Daniele, concerning the deconstruction of f on your previous slide, is it just solving a certain differential equation, or what?
Yeah, so basically what you need to do is you look at your curvature to form, which is not, you don't need it to be explicit, but for sure, for topological reasons, you know that this modulus is going to have some positive regions.
Yeah.
And what you do is you would like to compensate for the regions where this modulus is going to be 0. Okay. And what you know is you choose some function whose Laplacian is going to be negative in those regions. And the only restriction that you need to meet is the fact that globally the Laplacian of the function f should integrate to 0. But what you can do at that stage is to put the positive parts of the Laplacian in the regions where the modulus of the curvature is already positive, and therefore they are not destroying the global positivity of the Ricci curvature.
Oh, okay. Thank you.
Yeah. It's almost elementary, I would say. Yeah. Any other questions or comments? So my goal for the remaining, for the next 5 minutes is going to be to tell you how one can build the gluing neck, so how one can endow the cylinder of S3 cross S3 with the metric with non-negative Ricci curvature, starting from the family of interpolating metrics with the positive Ricci curvature on the radial slices. And in order to build the most complicated part of the gluing neck, where the twisting occurs, there are 2 steps that we need to perform. The first step is a reduction to the case where this family of interpolating metrics has constant volume form. And this uses an old idea which was introduced in the 60s by Moser. And once we have done this reduction to the case where the families, besides all the properties that I mentioned before, have also constant volume form, we can use basically a generalized work product ansatz where we just plug a suitably chosen warping function in front of the changing family of metrics G of t. And the possibility of doing of getting a Ricci non-negative on such an ansatz actually is borrowed from an earlier paper of Colding and Aaron dating back to approximately 10 years ago. So let me briefly comment on the choice coming from the first bullet point. So the effect of the reduction to constant volume form is to cancel out some of the potentially bad terms which come out in the formulas for the Ricci curvature of a metric in the displayed form. Now, this takes care of one of the parts of the gluing neck. And the reason is that the gluing neck that we build with this methodology is going to have both ends isometric to a cone over S3 cross S3. Possibly the radii of this S3 are going to be different. However, in order to complete the gluing, in order to complete the neck, we would like to match the geometry that we see on the other on the guy that we plug on the top of the construction, on the top of the family of all guys, in order to go on with inductive construction. And we would like to match the geometry that we see at the level of the gluing region of the all guys. And what's going to happen is that other deformation steps are going to be needed in order to adjust the relative size, roughly speaking, of the 2 cross sections, different to S3. However, the shape of the metric in these regions turns out to be a little bit simpler. And indeed, in order to take care of those regions, we not just need to employ a doubly work product ansatz in order to adjust the relative sizes of the S3 factors. Okay, so how much time do we have left? 10 minutes or less?
10 minutes.
Okay, so in the last 10 minutes, I would like to briefly make a brief overview about the asymptotic geometry of the counterexamples and its relationship with the finite generation. So let me briefly recall some of the terminology going into this subject. So in this setting, in the setting of non-negative Ricci curvature, a quite common procedure is the procedure of taking asymptotic cones or blowdowns, however you want to call them. Let me recall that an asymptotic cone or a blowdown of a manifold with non-negative Ricci curvature is just a pointed Gromov-Hausdorff limit, which is going to be a metric space with a fixed base point Q of a sequence of scalings of your original manifold with respect to a sequence of radii, with respect to a sequence of scales, which is fixed a priori and which is going to plus infinity. So the picture about regularity and uniqueness of asymptotic cones of manifolds with non-negative Ricci curvature turns out to be much complicated than it is in the case of non-negative sectional curvature. And indeed, let me comment on results that are as of today well known. So first, Perelman in 1997 constructed an example of a four-dimensional manifold with non-negative Ricci curvature whose asymptotic cone was not unique. Later, Chigger and Kolding constructed examples of manifolds with non-negative Ricci curvature whose asymptotic cones don't need to be isometric to metric cones. And more recently, Mengui pushed even further this idea and constructed examples of manifolds with non-negative Ricci curvature, such that for some asymptotic cone, this asymptotic cone didn't even need to be polar, where polar for a metric space with a fixed base point means that any other point apart from the base point should be an intermediate point of an infinite minimizing rate coming out from the base point. And the point that I would like to make, this was already mentioned by Aaron in his previous talk, is that often either the regularity or the uniqueness of asymptotic cones can force finite generation of the fundamental group. And in this regard, I would like to mention two theorems. The first one is a theorem of Sormani going back to 2000, which says that if all the asymptotic cones of a manifold with non-negative Ricci curvature are polar with respect to their natural base point, then the fundamental group should be finitely generated. On the other end, working at the level of the universal cover, we have a more recent theorem of Pan, which is saying that if the asymptotic cone of the universe, I'm going to give a simplified statement. His theorem is much more general in the end. However, let's stick to a simplified picture. So the simplified statement is the following. It says that if the universal cover of a complete manifold with non-negative Ricci curvature has a unique asymptotic cone, which is also isometric to a metric cone, then again, the fundamental group should be finitely generated. And let's see how our counterexamples are consistent with these two positive statements about finite generation. So the picture that you should have in mind about the asymptotic geometry of our counterexamples, starting from at the level of the universal cover, is the following. So I don't want to be precise on this. However, the way the construction works is that most annuli are going to be diffeomorphic away from very, very small regions to annuli or regions in S3 cross R form. And in order to describe you the asymptotic geometry of the universal cover of the counterexamples, I just need to tell you basically, I'm oversimplifying, how the radius of this free S3 factor behaves, and now the radius of the topological R4 factor behaves, where again, I'm viewing R4 as being topologically the cone over S3. So what happens in the construction is that the radius of the cross S3 factor is gonna scale invariantly shrink to 0 as we move towards infinity, and therefore, whatever asymptotic cone, whatever blowdown you pick, the contribution coming from this three-dimensional guy is going to completely disappear. At the level of the cross-section of the R4 factor, which we are viewing as being the cone over S3 again, this cross-section is going to scale invariantly oscillating between 0, which is the size of this cross-section at the intermediate scales of the gluing neck, at 1, which is the scale of the cross-section at the scales comparable to the geometric scales Rj, which I introduced in one of the very first slides, which are the scales where the gluing happens. So the picture is the one displayed on the bottom. You are going to be viewing the asymptotic at the level of the asymptotic cones R4 shrinking down to a cone, and then this to a half line, and then this half line is going to open up again. Very slowly give you a cone over a small S3 factor and give you back R4. Now, once you understand the asymptotic geometry of the universal cover, you can also understand the asymptotic geometry of the group. And if you take the quotient of the equivalent Gromov-Hausdorff limits, this is going to give you the family of asymptotic cones of the manifolds, of the quotient manifolds. And at the level of these guys, the remark, I don't have time to comment more on this, is that the asymptotic cones of the manifold with the fundamental group can include cones over length spaces. This was mentioned, if I remember correctly, by Aaron before. And these length spaces are going to correspond to different parameters, and the different parameters that you get are going to depend on the composition of the group gamma, which is the fundamental group we were starting with. And a key subtlety to keep in mind is that the cone point in these guys, which are all isometric to cones, is not always going to be the base point, and this is in full consistency with the positive theorem of Sormani that we discussed before. So in the last 2 minutes, let me just mention a few of the several open questions that remain open related to this conjecture of Milnor. So first, as far as you understand, the Milnor conjecture seems to be still open in great generality, even in the case where you make further restrictions on the geometric structure of your manifolds. So for instance, the Milnor conjecture is open even in the 4-dimensional Ricci flat case, and it is open if you make the further restriction that your manifold with non-negative Ricci curvature is going to be a Kähler one. On the level of the volume growth, this was mentioned before. So a theorem proved independently by Lee and later by Anderson says that if a manifold with non-negative Ricci curvature has the maximal possible volume growth, then the fundamental group is not only finite, but it's not only finitely generated, but it is indeed finite. However, the picture turns out to be much more subtle if you make the restriction on the volume growth at the level of the universal cover instead. So, and in which case, in the case where the universal cover of the manifold with non-negative Ricci has a clear volume growth, the Milnor conjecture is still open. And the last question that I wanted to raise was the question that was asked by Professor Gromov before. So the question is, broadly speaking, can one characterize fundamental groups of open manifolds with non-negative Ricci curvature? And this, again, let me point it out again, this should be compared with the theorem of Way, later improved by Wilking, which gives us a quite clear picture about the possible finally generated fundamental groups of manifolds with non-negative Ricci curvature. So that's all I wanted to say, and I thank you for your attention.